So, as usual, I kind of admire that XXCD has a sort of poetic expression, like depiction of Bayes' rule. It just reminds us that Bayes' rule mapped to some scenario in real life, it can have some unanticipated consequences or unanticipated interpretations. So I'll leave you to enjoy that. So this is what we're going to talk about. Graphical models, in fact, because of the sequencing of this class, you would have seen it. You have seen it in the mixture model class, where we observe some data X and they are generated from mixture component Z. So we're going to talk more generally about this kind of mathematical structures expressed in graphs. Starting from some motivation, and then we are going to say there are three kind of graphical models or graphs we will be talking about today until next Friday. And today our main focus will be on Bayesian networks. We talk about the concept. We generally touch or we quickly talk about sort of slight generalization of the notation to basically multiple instances of variables of the same structure in something called the plate notation, which the invention of which is tied to like our former colleagues in Canberra and still in Australia. And also we talk about how to reason about conditional independence through D-separation. So this, needless to say, will directly help your assignment 2 if you haven't got started in question 1. You can say that everything comes from the sum rule and the product rule, but yes, elevating our representation and using graphs has its advantages. So let's start from some brief motivation about why we need to encode dependencies in a rich graph structure. So if we think about image segmentation, the view on the left is essentially the view in, let's say, the 60s. If we have a toy image that are idealistic, what can we do with it, right? In image processing, you say, oh, we just look at the pixel value and assume similar pixel values sort of cluster together. And we get this, and the segmentation is perfect. But of course, the real world is quite far from that. And the way that the field of image processing deal with it is to do, say, post-processing, right? Let's talk about that. So let's say, well, this is still a pretty simple natural image, for example. It's simpler than if you're looking at me on a video. There are lots of colors and shapes, say, in the video lecture itself. But in this picture, there's just some grass, maybe 2 different kinds of grasses and 2 different horses. And ideally, we will want to, and the horses are more or less the same color, right? We will want to segment the foreground, the horses, and the background, the grass. And if we use this pixel clustering trick, what we get is the highlights, or basically the lighter pixels on the horses gets grouped into the background, right? The way the image processing traditionally deal with it is to use what's called morphological operators. Basically, look around the neighborhood of any pixel with a fixed neighborhood size and say, if, oh, most of my neighborhood is like some other class than what the plane cluster thinks of this pixel, then I swap it. Basically, try to make the segmentation smooth over like neighboring pixel locations. So that can work to an extent, but obviously it also has challenges. For example, for high-res image where these misclassified patches are big, then we're not going to be able to correct a mistake. And if our like it also depends on the morphological operator size. If it's too small, it undersmoothes. If it's too big, then it makes, for example, the whole foreground overly big. So therefore, there is, you may ask, right, how can machine learning help, right? So graphic models, or especially Markov random fields, as we will talk in some detail next on Monday, is a way to formally express the relationship, segmentation relationship in between pixels in the same neighborhood, and allows us to learn the basically strengths of statistical correlations, rather than, say, morphological operators, which is pre-specified, essentially a rule that's pre-specified. The second example is closer to what you might think in terms of encoding, explicitly encoding dependence and relations between variables. If you have read about Bayes networks in the popular press or the media, this will be also quite close. You might have actually seen this exact example. So here, let's say we have 4 variables. Each of them are binary. Let's say, right, so they're called cloudy, sprinkler, rain, and grass. We just abbreviate them with their first letter. Each of them have the variable false and true. Intuitively, if the sprinkler is on, then there's a high chance of the grass being wet. The same with raining. If it's raining, the grass is also wet. And whether to turn on the sprinkler or not, or whether it rains or not, depend on whether, it's cloudy in the sky. So we've learned conditional probabilities and Bayes rule. So here's the way to express this formally, right? So we can say that the prior probability of whether it's a cloudy day, it's point A, right? It's point A being cloudy. This is certainly not Canberra. We might be the reverse. Let's imagine, let's say England, right? So this might be true. And then we can encode the relationship between whether to turn on the sprinkler, given whether it's cloudy in this conditional table, right? So when it's not cloudy, we turn on the sprinkler half the time, half the days. When it is cloudy, we don't turn on the sprinkler because evaporation is low, right? Same goes with raining, right? So when it is cloudy, right, the probability of rain is 0.8. When it is not cloudy, the probability of raining is still 0.2. It's also all seen like raining with a perfectly in like bright sunlight. So weird things happen. And then in terms of whether we observe the grass is red. So here the scenario can be that we went home and saw that the grass being wet. We did not exactly observe whether the sprinkler has been on sometime during the day, or whether it has rained, or whether it has been always cloudy or not during the day. Because let's say I'm shut in an air-conditioned office all day, right? So this conditional probability table simply says, well, if the sprinkler hasn't been on and there has been no rain, then it's impossible, or with probability 0, the grass is wet. If both are on, then it's almost sure that with 99% probability that the grass is wet. If only one of them is on, then the grass is wet with 90% chance. Right, so this is how we use a graph an example of using the graph to encode intuitive dependencies of random variables and observations. Right. What this toy example also means is the alternative of expressing this real-world knowledge as a graph is to fully write out the joint distribution of these 4 random variables, right? In that case, if we write out Bayes rule, it's basically, we can start from the node cloudy, and then essentially successively apply Bayes' rule on conditional probabilities and get essentially each successive variable, rain dependent on cloudy, and then sprinkler dependent on rain and cloudy, and then grass being wet or not depend on all three, right? So if we draw an arrow for any, like from any of the conditioned variable to the variable we're modeling, then we end up with this graph with two extra green edges rather than this particular one. So this is a general and indeed correct representation or decomposition of the joint probability, but this one is slightly more succinct, right? So we're talking about 4-node networks. You might say, oh, I'm perfectly able to model this fully connected network with 6 links. If your network is 400 nodes rather than 4 nodes, we won't say that as confidently, right? So just to compare and contrast the two different ways of expressing the joint probability, right? If we are going to compute, for example, what is the marginal probability of a wet glass for the fully connected version, generic network, we need to basically jointly marginalize out 3 variables and then based on the sum rule get the P of W. In the factored case, we can actually eliminate the variables in stages. Basically, we can marginalize out this cloudy variable without touching this last term, right? And then we marginalize out the sprinkler and rain. We'll see more about this. So we've already seen our first Bayesian net. Let's formally define it with some terminologies. So one thing that I will say about the SQL in graphical models is that there are a lot of words or new terms. And I would say it's important to grasp or comprehend what exactly these terms mean. And sometimes they may mean stuff that's not completely it doesn't coincide with their common meaning, right? So graphs, like the absence of edges are more important. They encode conditional independence, but we don't talk about the implied conditional dependence, right? And for some of these new terms, you can operationalize or basically use them to reason about things fairly readily. For some of those terms, there is basically a few steps to map from the concept to the practice, such as in the question 1 of assignment 2, where we might have sort of intuitively grasp what is estimating, say, a probability table is, but to turn it into code, there is some level of notation which the question 1 handholds you through, right? So, okay. So back to the main content, right? So probabilistic graphical model is represented as a graph, right? So there are nodes, and the nodes are random variables. There are edges that express probabilistic relationships. Here I'm intentionally being general because there are 3 different kinds of graphs with different probabilistic relationships. And the entire graph is intended or designed to capture structures or different factorizations in the joint distribution of all nodes. Yeah, okay, we'll talk about this a bit more. So for the Bishop book and the purpose of this class, we're mainly concerned with 3 types. The first is directed graph, basically Bayesian networks. That expresses causal relationship between variables, right? For example, in the rain and sprinkler case, we can say that raining causes the grass to be wet. Same goes with sprinkler, The second kind is undirected graph or Markov random fields. It expresses soft constraints between variables, such as the image segmentation case. We can say that neighboring pixels tend to have the same label most of the time. But if you would need to make an exception because the image needs to be segmented anyway, and the segmented object needs a boundary anywhere, then you pay a cost, right? That are formally expressed in the energy function of MRFs. So the third type is called factor graph. It is a representation introduced not to describe say, natural phenomena or phenomena that happens in our real life. It is designed to help us solve inference problems, right? So we can derive factor graph from Bayes network and Markov random field. And in here, I think for the graphical model section or chapter, it's particularly important to emphasize basically the notion of inference and learning. So in fact, inference is a fairly loaded word in and around the machine learning literature. If you read blog posts, some of them will just call like training a machine learning model like inference, right? Well, for the purpose of this particular chapter and for most of the Bishop book, we're going to basically assume that inference is the process of computing the posterior distribution of one or more subsets of nodes. It might be conditioned on values of another subset of nodes, right? And here we're assuming that the conditional probabilities or the parameters of, let's say, the Bayes network or Markov random field is known, right? Known graphical model, and the graphical structure is known. Related to that, so that there is a task of learning the parameters of graphical models with a given graph structure, which is in your home assignment, right? And we do this, we estimate parameters from a data set of observed variables. So if all of our nodes are discrete, we can just think of them like we know that estimating the parameters of a binomial or multinomial distribution, the maximum likelihood estimate, we're not talking about prior here, is simply the fraction of data having the corresponding value, right? So we just extend the notion there. So as we have learned in the EM section, inference or computing basically in the EM, the gamma parameters is a key step in learning, right? Since we will not be touching on like exotic distributions, at least for the purpose of this class. For example, learning or maximizing the likelihood by tweaking the parameters is usually simple. Let's say for exponential family, for Gaussian distributions, estimate the mean and variance. For discrete probabilities, just count up the probability tables. They rely on inference. Yeah. And so as you will see, we will basically mainly spend our time on inference and not learning, which assuming that learning can be done and you kind of, it's easily done after you solve the inference problem. All right, so what are the overarching goals and advantages of working with graphical structures in probabilistic models, right? So one advantage is to visualize the structure of a probabilistic model. For example, some of the early applications of Bayes nets are, for example, troubleshoot why the printer failed, right? A printer is machine with many different components, and it's connected to other things. The printer might fail because of the connection to power is out. Right now, we all use network printers. So maybe the network configuration is out, or there's out of cartridges, and some of these factors sort of influence each other, or maybe you didn't load the right paper into the right tray, and so on and so forth, right? And the visualization aspect is quite important because it allows us to actually design this model and communicate it to non-machine learning specialists, right? And people might come, such as, say, doctors, infrastructure designer, and so on. They can come and say, oh, the model should express this relationship rather than that relationship, or there is a missing relationship, right? So therefore, it's useful for designing, motivating, and auditing, like checking new models, like and the probabilistic relationships. So the second advantage, which we will look at today, is so important probabilistic properties such as conditional independence can be obtained by inspection of the graph, looking at the graph or checking the graph via a computer. So this is more for people designing or running machine learning algorithm. So next Friday, we're going to see that, right, so complex computations required to perform inference, assuming that the graphical model is non-trivial, and learning in sophisticated models can be expressed in terms of graphical manipulations. So, and if we think in this way, we don't need to work, like, basically the argument is that working in terms of the graph is sort of better for us to grasp what's happening during inference. Yeah, and it says that the underlying math is sort of carried along implicitly. So one example for this is, let's say, image segmentation, right? For those of you who are taking computer vision this semester, you probably already worked on this. For those of you who have not, basically, if we have a pixel grid in an image, right, and each pixel have some probability of being, say, the foreground or background, and we so kind of want different neighboring pixels to most likely belong to one class, but we do need to separate the whole image. So, and we know that if we flip the label of a pixel, let's say here, then it will influence what these other pixels get flipped or not. As you can see that these pixels sort of influence each other, like they can influence each other in a way that you can sort of flip the label back and forth. Coming up with the best set of foreground versus background labeling for these pixels is non-trivial, right? Especially if you imagine this grid being, say, 200 by 200 or even like more than 1,000. And this is actually done, right, in modern mobile phone software, right? If you have a, let's say, Google phone from Google, Apple at least, it does sort of, it is able to segment your, like the person or the subject versus the background, and even give you cinematic effects. For example, we're using Teams and Zoom, right? The computer is able to basically segment me out of my office background and plant a different background. Of course, in here, the computer has a bit more information because it's a video and I'm moving, but also not moving too much, and the background doesn't move. All right, so that's a sidetrack about segmenting images, but here is what Bayesian networks do, right? So let's dive into Bayesian networks. So assume we have 3 nodes, A, B, and C. The joint probability is just expressed like this. And then using the product rule or base rule, we can trivially write out basically factors if as C conditional on A and B times the join of A and B. And we can do this once more between the nodes A and B, and basically we factor the joint distribution using base rule. We've done this a few times in the semester. Basically, we have A conditioned on nothing, B conditioned on A, and then C conditioned on A and B. So this is a general, let's say, general representation of the joint distribution of the three variables. Also, for the sake of just simplicity in talking about these variables, throughout this chapter, we're going to assume that A, B, and C are discrete variables, having a small number of distinct values, right? Or at least finite number of distinct values. So we note that the left-hand side of 8.2 is symmetric, but the right-hand side is not. What this means is, although this factorization is fully general, but we did commit to an ordering, implicit ordering of the variables that make the right-hand side no longer symmetric, right? And then we can intuitively write, based on the conditional dependency relations, that A doesn't condition on anything else. B and C are both conditioned on A, so as reflected here. In addition, C is conditioned on B, right? So these arrows represent this implicit choice of ordering, right? So for the same joint distribution, it's possible to have different orderings. For example, if we flip the arrows, every single direction of every single arrow, it's still a valid representation, and we can essentially just, flipping the order of A, B, and C in 8.2, and it's still a fully general representation. We can also have different decompositions and different graphical models, right? Okay, so we're looking at the same small graphical model for a general case, right? If there are k different variables, right now let's assume that the lower numbered nodes are sort of first in ordering, in that they condition on less things. We just, for example, if we have k variables, x1 through xk, we first pull x1 out, and we condition x2 on x1, x3 on x2 and x1, and so on. So this decomposition is general for any k variable joint distribution. And the graph is fully connected in the sense that if we ignore the direction of the arrow, there is a link between any pair of nodes. We can intuitively see here, right? So a higher numbered node is connected to all of the other nodes who have a lower number than it, right? K is connected to the rest of the k-1 nodes. K-1 is connected to 1 through k-2, and so on. So far, we haven't gained anything. We were just doing the sum and product rule exercise, right? So right now, let's see if we can say we are no longer interested in modeling fully general PDFs, because that does not encode, let's say, structure in the real world, right? Whether, for example, the power supply to my printer fails or not, is quite unrelated to whether the toner has ink or not, or whether I've loaded the paper correctly, right? So let's say for real applications, our distributions won't be fully general. And so let's say now we have a network, or we have a joint distribution that's defined over variables x1, x2. So what's the largest number? Oh, x7, okay. So we have a 7-node network, and we know that it factors like this, right? So one thing to note is that this factorization is quite hard to work through for us mere mortals, because, hey, it's a very long expression, and yeah, my working memory is limited. I can't possibly remember all of this. And yes, encodes dependency relations, but yes, it's not so intuitive. So now given that we learned what Bayes network, how to express things in Bayes networks, let's just try that, right? So we draw a node for each of the conditional distribution associated with a random variable. What this means is we look at each of these terms. For every node in the front of each term, we draw a node, right? So there are 7 nodes, we know. But in order to draw a graph, we need to basically place these nodes appropriately and draw edges on them, right? So that the second part is the crucial part. We draw an edge from each conditional distribution associated with random variable to all the other conditional distributions which are conditioned on this variable. So it's a mouthful. What this means is basically we take any node, let's say, x5, and we look at which other nodes is conditioned on x5, right? You say, here, only x7 is conditioned on x5. So now we know, like there is a link from x5 to x7. So that's good, right? We can also look at one of the lower number nodes, right? Let's say x1 is not conditioned on anything, so therefore it gets its own node with no incoming edges. x2, same thing, right? So it has no incoming edges. But let's figure out which nodes are conditioned on it and then just draw the corresponding edges. We're now drawing x2, so x4 is conditioned on x2. That's it. Right, so here's the edge. If we do so for x1, for example, then x4, x5 are dependent on x1s, right? So therefore, there are 2 outgoing edges. And note that x6 and x7, the latest nodes, they are not directly dependent on the first 3 nodes. Unlike the most general case, they're only dependent on x4 and x5. So yeah, we can appreciate that this expression is quite a bit shorter than the fully general one. So what this also means is it's the absence of links in the graph, such as x1 and x7, that conveys interesting information about the property of the class of distributions. It's more the absence rather than presence of edges, because by default, every lower number nodes gets to point to every node that has a higher number than it. Right, so another word about this node, like terminology of a lower number node, this is consistent just for this book, right? If you look at other literature, you can number nodes sort of in a completely reverse way. You can say lower number nodes are pointed to by higher number nodes and it still holds, right? Or you can decouple the numbering, which is actually relevant from the dependency relationship, and that's also okay. So the next question we ask is, since we have just gone this way from the joint distribution expression to the graph, can we do it the other way, right? If we're given a graph, can we come up with a joint distribution, right? So the way to do this, so this slide is kind of lots of words because it has included the exact words from the last slide. So the same deal, right? If we have 7 nodes, we know that our joint distribution are going to have 7 random variables. And the question is, how do we turn edges into conditional probabilities, right? So for each node in the graph that does not have a parent or does not have an incoming edge, we are just going to sort of write them out as their own, right? And then for each random variable that has incoming edges, we're just going to make it conditioned on the nodes that points to it, right? So x4 has 3 parents, x5 have 2 parents, 2 parent nodes, x1 and x3, and x6 has 1 parent, x7 has 2 parents. Then we're done, right? So this is a mechanical exercise. And you can, when you're performing inference, you need this expression when you're sort of examining a graph and talking about it with your friend, you need the graph, right? So would any graph fit, right? Not, obviously not, right? So one notable restriction is that the graph here we assume are directed. The direction of the arrow encode conditional dependency or conditional probabilities. So the entire graph must be directed, but doesn't have directed cycles, right? So undirected cycles are fine. So basically, if we ignore the edge direction, and we can basically say we travel this way, and we can get from one node to the other node. But directed cycles is not, because we can't have P of xk given xj, and then P of xj given xk. So that breaks, let's say, the intuitive ordering that we want, right? Right. Yeah, to paraphrase this, because this directly acyclic graph is so important for base nets, you shouldn't be able to find closed paths in the graph if we move along the directed edges. So this is equivalent to the node ordering that we talked about, right? This is equivalent to their existing ordering of the nodes such that there's no edges that go from any node to any lower number nodes. So we are only conditioning on lower number nodes. So this is also a way to check whether we've sort of drawn the base net and write out the conditional distribution, factorisation of the joint distribution correctly. It's a necessary condition. It's not a sufficient condition. So you may say, right, so we now assume, let's say each node takes a number of like discrete values. What about, yeah, can we have continuous nodes? Yes, we can. I forgot if I said so, but for example, if some of these nodes are continuous, let's say P of x6 over x4, if x6, if this thing is conditional Gaussian, right, mu and sigma, like mu of that are parameterized by x4, then essentially we have multiple slices of like the distribution of x4 will be different depending on what x6 is, and this is the probability, right, of either the joint or the conditional. You may say, can we have vector valued nodes? Yes, we can, right? So suppose we have an x8 that has exactly the same dependency as x7. We can actually group them into a node, the same node x7 tilde, which essentially says, right, we have a vector valued node. Each component has the same dependency, right? So you will say that if for any joint distribution we would like to factor, we try and write out an expression like this. That's quite tedious, and it gets sort of longer than the piece of paper we can have for our screen fairly quickly, right? So in general, you can write out succinctly the notation over a graph is, if we define the parent set of node K as PA of K, then the joint distribution is simply written out as a product of each of the variable's condition on its parent. Right. So the modeling savings or advantages is that if we have the parent set equal to all of the nodes that are numbered lower than this node k, then we achieve no savings. If the parent set is smaller than all the lower number nodes, then we have a sparse graphical model with missing edges, which is good. And the joint distribution is no longer general, and it encodes assumptions of, for example, conditional independence. In the grass and sprinkler and cloud example, in here it implies that whether the grass is wet is independent of whether it's cloudy if we already know whether the state of both sprinkler and rain. We'll get, well, yeah, we'll spend a fair amount of this on these kind of statements today. So you may ask, if we just write out the probability in this way, is P of X properly normalized? Because we've kind of hinted from Monday's session or the sampling session that a lot of times P of X is not properly normalized and we can only evaluate the optimal normalization. The good news with DAGs or BaseNet is that this is actually properly normalized, right? Because of this sum rule, right? If we basically, for each of these terms, we know that like P of X is product of these conditionals of the same form. We also know that for each of these conditionals, if we sum along the variable in front, it's properly normalized, right? So the conditional probability themselves are properly normalized. We can find an order of the nodes, actually from low to high, that if we sum over the high number nodes first, each of these terms will just normalize itself to 1 until we get to like we essentially sum over all of the x's. So we repeat the summation process until no left. Then we can show the P of X is normalized. So this is a detail, but it gives us confidence in the sense that this kind of decomposition gives us proper probabilities, which is quite important sometimes. For example, if we're sampling from this, we know that we don't need to sort of post-process the sample somehow or estimate additional quantities. So that's sort of in a nutshell how we represent like what the language of BaseNet looks like, right? The next thing we will see is what's called a plate notation, or how to make BaseNet more succinct if there are multiple copies of the same variable, such as, let's say there is a time series, or in typical case, right, in the regression and classification case, we observe, say, multiple target variables in our training set. We denote them as T1 through Tn, and they all depend on this, if we're being Bayesian, this variable called W, which is the weights of regression, right? So the book talks about Bayesian polynomial regression, but this notation essentially applies to many of the vanilla machine learning models we looked at. So an alternative representation, instead of saying T1 is the variable and ... Tn, which is quite a handful, and it's difficult to draw if we have more than just W and T, we now just draw essentially what's called a plate or a square outside of these T's, saying that these T's are indexed by small n, and there's a big N copy of it, with essentially the same dependency indicated by the same arrow. So that's helpful. The book proceeds to present basically a more complete picture of polynomial regression, right? So this part between W and T sub n is the path that we just looked at on the last page. The book also says, well, we can include essentially the random variables are the circles. The deterministic variables or the parameters or observations are small solid circles or dots. So there is a prior or regularization parameter alpha for the W. Inputs are x of n's, and then because it's a regression, there is the noise level called sigma squared. And we can basically see W's. Tn is conditioned on W, but it's also conditioned on x of n. It's also conditioned on sigma squared. There's n copy of it, therefore it's multiplied. So this is the this is the posterior. And then W is conditioned on the prior alpha. So that works. So during training, we observe xn's, we already said, and also tn's, right? So we can shade the observed random variable. We already saw this representation in, let's say, Gaussian mixture models where the x's are observed variables, where the hidden components are clear variables. So this is, at least for this class, we stick with this convention. If you're reading some random literature, the conventions might be different. For example, I don't see this small solid circle as a convention a lot in the community, so it's worth paying attention to what's different. One advantage of learning through a textbook is that the conventions are consistent with each other, and we don't need to spend time context switching, which is not true once you start reading papers or random blogs online. We don't really need to cover this, like if we do, model prediction and so on. You should be able to just read this and understand it based on what we covered so far. So it's worth saying that Bayes nets, they are generative models in the sense they allow us to draw samples from a joint distribution. We can see this by looking at this general expression of the product of conditionals of every variable condition on its parent set. This approach is called ancestral sampling. Basically walks through each node in order from lower ordered to higher order nodes, x1, x2, all the way to xbk. It draws lower number nodes first. So in order to sample the join, we need basically a value for each of these variables or components. X1 is guaranteed to have no other parent, so we can just draw from Px1. And then if X2 doesn't depend on X1, draw that. So draw P of X2 or draw P of X2 conditional on X1. Here we're assuming that X1, X2, and so on are multinomials or binomials, so it's easy to draw without needing the, say, sampling tricks that we talked about on Monday. And then once we get to X sub K, we should already have all of its parents, so we just draw on the conditional probability with the condition on the parent values. Probability of X of K is also just a table of probabilities. And if we would like to obtain samples from marginals, let's say arbitrary marginals, P of X2 and XK, we just throw away all the other variables and then retain X2 and XK and tabulate, right? So that's simple. In a typical observation application, the way we use these Bayes nets is that the terminal nodes are observed. So terminal nodes are the ones that don't or leaf nodes, so to speak. They don't have any descendants. So they're typically observed, but they have a complex distribution. And the parent or grandparent ancestral nodes, they are not observed. The lower number nodes, they are latent variables, they are not observed. And we can probably hypothesis about their prior distribution better because that tend to be simpler. But the trick here is to infer from observed nodes, such as in here, the image is observed, right? But if we're dealing with computer vision again, then the object and its position and orientation is unobserved. It is what we desire to infer, right? So in general, Bayes nets represent a causal process. So there is a whole causal inference literature headed by Turing Award winner Julia Pearl that talk about how you can properly do causal inference on a Bayes network, or causal network. We are not going to get into that, but hopefully learning the basic language of Bayes network makes it easier for you to learn those. So we would say that in general, Bayes nets are generative models, but polynomial regression isn't. You can make it into one, but it involves more nodes and complexity. So the latent variables doesn't necessarily need to have a physical interpretation. It can be just instigated for representational convenience, right? And computation in order to make the computation tractable. We will skip this. So let's spend, well, we have about 35 minutes left. Hopefully spend the next half hour talking about conditional independence, because this is quite an important tool for us to parse and use Bayes nets. So what exact conditional independence are encoded by these missing edges, and how do we get them out from the graph, right? So let's first define conditional independence, and then we go through a number of representative toy graphs to reason about what are the common patterns, and then we come to a general statement, right? So if for 3 random variables, A, B, and C, if the conditional probability of A conditional both B and C is equal to the conditional probability of A given C, then we say that A is conditionally independent of B given C. Right, so this is easy to see, or one intuitive way to reason about this is that if we have, let's say, we have the conditional probability table, right? Let's say B of C and A here takes the value of, let's say, 0 and 1, and B and C take, say, maybe 0 and 1 too. Okay, 1, 0, 1, 1, right? And then, so this is basically a 4x2 conditional probability table, right? And similarly, we write out the probability of A given C itself, which is just 0 and 1. Actually, I wrote it. It's probably more convenient if I wrote it the other way. So let me just change it. It's like 0, 0, 1, 0, 1, 1, 0, 1. Right. So we can see that, well, here, the top half has C equal to 0, bottom half has C equal to 1, right? In here, we have some number like P1 minus P, and then Q1 minus Q, right? So if these numbers are exactly the same for each of these cells, right? If this is P1 minus P and this is P1 minus P, then and same holds for the bottom half, then this statement here holds, right? So it's just to say the above equation must hold for all possible values of C. And then the consequence of this, we can basically use the Bayes rule to derive this. The joint probability of AB given C can be factorized into A conditional C times B conditional C, right? Because the first step is Bayes rule. The second step uses this statement above. All right. The conditional independence implies structure of the Bayes net. The model is vague. Let me just say the Bayes net. The computation we needed to perform inference and learning is there's some savings, right? As you can see that this is, say, like a 4x2 probability table, but this one is just a 2x2 probability table for binary variables. Again, we are talking about conditional independence and not conditional dependence. So there's a couple of rules of conditional independence. It's symmetric, which is intuitive to see. You can all go verify this using simple probability sum and product rule itself. It also decomposes, basically, the joint of two variables have the same conditional independence. It means we can write them apart. So I'm not going to go through these ones. They might be useful to refer to if you're giving an exercise of this to reason about conditional independence. Our focus is to get this conditional independence out of graphs. So we're going to look at three node toy graphs, right? The goal is to infer conditional independence of A and B. So the three nodes are called A, B, and C, as you can see. So we assume right, so is A and B conditionally independent, given C or not given C, right? And the larger goal is to extrapolate from these simple three-node patterns, spot general graph patterns that we can use to reason about conditional independence in general. So here's the fully general fact, right? So in this particular graph, right, based on how Bayes nets are constructed, we know that the joint decomposes into C is the lowest number node here. So P of C itself plus A conditional C and B conditional C. So in here, we also inherit the notation that C is unobserved or latent, right? So if we don't observe C, we basically marginalize we wonder if probability of A and B itself, the joint is independent or not. If they are independent, then it should factor into P of A times P of B, right? Because of this expression here, we know that in general, they are not conditionally independent given nothing, right? Now, if we condition on C, right, we now wonder if P of A and B given C is can factor into A given C times B given C. This is true because this middle term, right? So we can use Bayes rule in this term, right? And use the factorization on this page, we can get that A and B are conditionally independent given C. So if C is the parent of both A and B are conditionally independent given the value of the parent. The graphical interpretation of this is we now call this particular pattern tail-to-tail pattern. Basically, there are two sibling nodes sharing the same parent node. Right. It's called tail-to-tail pattern because the node being connected to C is connected to the tails of arrows in the path. Right. So the presence of the tail-to-tail node C leaves, well, it renders A and B dependent on each other, which intuitively makes sense because otherwise it will be just completely like disconnected and hence independent. And conditioning on C blocks the dependence between A and B. Right, meaning, well, going back to our toy example, knowing whether it's cloudy or not renders the probability of the sprinkler being on or not and raining or not independent. All right, next pattern. So you say, well, that's not the only way that three nodes can be connected. So here's the next one. We make the three nodes in a chain and then ask ourselves about the middle node, right? So this is called the head to tail pattern because node C is connected to the head of the arrow in one side and the tail of the pattern on the other side. So it factors like this. A is the lowest numbered node. C depend on A and B depend on C. All right. And then we can say that if C is unobserved, does the join of A and B factor? The short answer is it does not, because in this pattern, we can marginalize over C, so C vanishes, and then B directly depend on A now. Right, does not hold. However, if C is observed, and we can condition on C based on the pattern above and applying Bayes' rule, so this term comes as the join of A and C, and then use Bayes' rule of that, it converts to P of A condition on C rather than C condition on A in the definition of Bayes-net, right? So when we use Bayes' theorem, A and B are conditionally independent given C. So this is kind of intuitive in that, right? So in the cloudy and grass example, if we know whether the sprinkler is wet, is on or not, then whether the grass is wet or not is conditionally independent with whether it's cloudy or not. So that's head to tail pattern. The third pattern is the trickiest. It's called head to head pattern. It decomposes like this. Basically, there's a node C, and then it has two parents, A and B. Right. So A and B don't have any parents. It just comes out as its own. And C is conditioned on both. Right. So if we marginalize over C when it's not observed, and see P of the join of A and B, if we marginalize over C, it only works on the last term. It normalizes to 1, and then it comes back to the original two terms, the product of marginals. Therefore, A and B are independent if C is unobserved, right? So if I, like, there are two parent nodes, if there is the children node is unobserved, they are, well, they are modeled independently. So it's more interesting when C is observed, then what happens in this head-to-head pattern? So we condition the join of A and B on C, plug in the expression for the join probability. We now arrive at, right, right, so if they were independent, the expression should be equal to A condition on C times B condition on C, but we cannot, right? Therefore, A and B are not conditionally independent given C. So This one is a bit counterintuitive because knowing the value of the children node A and B are no longer conditionally independent, right? Knowing the value of the children node actually couples the distribution of A and B versus not knowing it, like sort of sets them free. So let's look at this a bit more and then define some terminologies, or going back to the terminology we defined in the first case, and then we look at an example. We can also go back and use the sprinkler, rain, and grass example. I leave that to you to sort of exercise because we talked about that enough. So the graphical interpretation of this head-to-head pattern is as follows. In both graphs, there's a path from A to B. The node C is called having a head-to-head pattern, basically a common child node with different parents. And then the presence of the node C makes A and B independent. And then the unobserved C blocks the path from A to B, but then the observed C unblocks the path from A to B. Right. So depending on the, well, summarizing on the three patterns we talked about, depending on the direction of the arrows, the observing C either blocks or unblocks the conditional dependency. Right, so the graphical independent interpretation continues. Basically, conditional C unblocks the path from A to B. Furthermore, if we have this pattern, which is similar to the one on the left, except it's a bit more complex. If in here it's the node E that's the common child. If node C is the descendant of E, actually direct children or even somewhere downstream even more, knowing this head-to-head pattern E or it's any of these descendants actually unblocks the path, right? So formally speaking, and head-to-head paths will become unblocked if either the node or any of its descendant is observed. So this is the phenomena called explaining away, just to sort of give you a bit more intuition about this head-to-head pattern and how counterintuitive it can be, but how you can intuitively interpret this, right? So suppose now we have a three-node graph exactly in the way that we were setting it up, except now it's called the battery, fuel of your car, and the fuel gauge, right? So you can say that, hey, the electric fuel gauge is reading like basically high or low. When it's low, you might need to go for a refill because your fuel is running low, which is a common scenario. Or maybe actually your battery is malfunctioning, which is an uncommon scenario, but it can happen, right? So this represents the real life dependency, and it kind of makes sense. Right. So if you read the corresponding textbook section, it contains the calculations. What it means is, okay, if we don't know whether the fuel gauge is low or not, battery and fuel are sort of driven by different physical systems in your car. They're sort of independent of each other. If we know that the gauge is low, however, then we need to blame either battery or fuel, right? And do something, right? Need to act. Let's say we know that the fuel gauge is low and the battery is low too. Intuitively, well, like just sort of in real life, one intuition you might be able to relate to is two simultaneous failures of independent systems are rare, right? So if rarer than them failing sort of just on their own, one of them failing. Therefore, if the fuel gauge is low and I know that the source of that failure or needing to act is because of the battery, it actually is, it means that it's less likely that I'm running low on fuel. So this is the phenomena that's called explaining away, right? So if basically if this I know is low, battery is low, then the chances of fuel being low is, or actually there's more chance of the fuel being fine or high. If you manipulate the conditional probability tables in the book, as the book does, you can verify this intuition. This is generally called the phenomena of explaining away, right? Knowing the children, one factor, like so sort of the two factors are explaining each other away. Same goes if we already know that the fuel is low, it might have caused the gauge to have a low reading, and it's actually less likely for the battery is low. You can do the calculation the other way around using the same model presented in the book. So what have we done? We claim that we have examined all the relevant patterns, right, for conditional independence. So what we did is we examined configurations of 3 variables, where the directions of conditional, like the arrows, is head, tail, and tail, tail, and the variable being observed or unobserved. We talked a bit more, a bit more time about the head-head junction and the phenomenon of explaining away. Now we are ready to sort of jump, start from this 3-node little network to arbitrary based networks, right? So this is the term called D-separation, stands for nodes being directionally separated in a base network. Directionally, it's easy to understand. The arrows have directions, and in here, separated means sort of conditional independence, right? And here's how we do it. We define a blocked path being essentially an observed or shaded tail-to-tail or head-to-tail node, right? Or an unobserved head-to-head node. And moreover, the descendants of this head-head node, HH node, is also unobserved. And the notion of D-separation is defined as follows. So now we consider a general graph where we have a set of nodes A. Now, like instead of small a, we now write a large A. And the set of nodes B, I drew a cloud because there's multiple nodes in here, and a set of nodes C, right? That are non-intersecting. They're arbitrary but non-intersecting, right? So have 3 sets of nodes. There might be other sets of nodes in the graphical model that we're not talking about, and so on and so forth, right? So we consider all possible paths from any node in A to any node in C. So we're just tracing, like, okay, so any node in A to any node in B, right? So here, let's say like that, or maybe like that. They're connected in different ways. So if such a path is blocked, right, so we consider such a path to be blocked. Oh, okay. If we include a node in C that has a head-tail or tail-tail pattern, or the node in C is an head-head pattern, but it's unobserved, or any of its descendants are unobserved, right? So in here, we need to reason about C and also reason about its possible descendants. So here's the, so far this has like no new content. We're just looking at sets of passes rather than one pass, right? The jump off from one like 3 node patterns to the entire network is now, if all paths are blocked, then A is de-separated from B by C, or conditional on C. And the joint distribution of all the variables in A is independent of all the variables in C conditional on C, on B conditional on C. So that's de-separation for us. Yeah, you get to exercise this in the beginning of question 1 of assignment 2. As you can see, for a 10-node graph, it's still pretty easy to work it out, right? So here are some examples that's slightly more than 3 nodes. In here, we're concerned with the de-separation property of A and B given F. In here, F is unobserved, and F is a TT node, like we're looking at, and there is only one path from A to B. So therefore, A and B are not conditionally independent given F. And then now we also wonder whether A and B are conditionally independent given E, all right? So in here, E is a head-head node. So this should be fine, but one of its descendants are actually observed, therefore unblocking the path between between A and B. So this is also not conditionally independent. So now let's swap which node is observed. So A and B given, right, so here it should be F clear, I would say, like unobserved. And here E unobserved. So if we have F observed, it's a telltale node, because then it's independent. Furthermore, the path from A to B is also blocked by E, which is headed node. So, and its descendant is also unobserved. So, so this basically changes the like observing F and not observing C changes the conditional de-separation property. So in general, the results in the literature shows that if a probability distribution factorizes according to a directed acyclic graph, okay, so for a base net, and for disjoint subsets of nodes A, B, and C, if A is de-separated from B and C, then the distribution satisfies these properties. Basically, this established the correctness of reasoning about de-separation in the previous few pages. And it's also the other way around, right? So we may ask ourselves at this point, why is conditional independence and factorization relevant, right? So conditional independence is usually what a domain expert knows about the problem at hand. So you can present, let's say, the printer debugging scenario. You can present them with a graph. You can also present them with derived conditional independence statements, and that will influence the design of your base net. And they are needed for computing the joint on marginal distribution in order to do that efficiently. So this relationship between conditional independence and factorization provides the expressions of P of X for computation, right? And as we will see, the computation is executed on local conditional independence statements. So more about that on next Friday. So we're nearing the end of this series of concepts in graphical Bayes networks. So here's a general picture, right? Taking a step back. We are looking first at the general joint distribution P of x for some non-trivial number of random variables. And if we have a graph or Bayes network of these graphs containing these variables, we can look at this graph as a filter, right? So from the general joint distribution, passing through this graph, only a subset of valid joint distributions are left. Right. So basically, like this DF set contains any joint distribution that factorizes according to the graph, and vice versa. Right, the D-separation theorem says it's the same set of distributions DF that will be allowed through this filter. So that's all. This is just to reiterate that basically a graphical model expresses a subset of joint distributions satisfying conditional independence criteria. It can also be written out in a particular factorization form. This picture is useful as we look at Markov random field on Monday. So in summary, we covered what are graphical models and Bayesian networks. We looked at what the nodes and edges mean. We looked at how to reason about conditional independence and factoring the distribution. Is there any questions so far? Yeah, no, Hinton says I'm not. Yes, right. So, okay, bear with me. So no, to answer Noel's question, I think the second half of the answer, the more important part of the answer is in next time. Basically, we can look at directed graphical models as sort of filter on, basically the factorization. Right, the DF, I think, represent, for me, factorization of the joint, and the graph is conditional independence. And next time we will see, basically, here's the spoiler. Next time there is an exact picture like this, basically for Bayes nets. We represent a certain set of factorized distributions. For MRFs. We represent another set. There's intersections, but there are things that can be filtered through Bayes net that cannot be filtered through MRF, and vice versa. And there are stuff that cannot be represented by either one. Yep, I would say look at, so that will be figure, yes. Okay, figure 8.34 is what we will look at next time. Yep. Yeah, thanks for the question. That's all. See you next time.